basic example of ideal. But this is basic obviously. These examples are very important for any competitive exam. Let's see this example at first. Which are ideal in the polynomial zx? Polynomial with even constant term. We have to check, is this polynomial with even constant term is ideal in zx? Polynomial with even constant term means px equal to anx to the power n plus a1x. Here the constant term be even. The polynomial is look like this. We can write it as easily x times qx plus 2k, where k belongs to integer. Actually the form of the polynomial will be this type of form. To prove ideal, at first we have to check subring test. We all of us know for subring test, if the set S is subring, then for all AB belongs to S, their difference also will be belongs to S and their product also belongs to S. Consider two arbitrary polynomial P1x and P2x. P1x is look like x q1x plus 2k1 and P2x is look like x q2x plus 2k2, where q1x and q2x be polynomial in zx. Then their difference would be x q1 minus q2x plus 2k1 minus k2. And obviously this would be belongs to the set capital S, because S contain such polynomial whose constant term be even, and P1x times P2x equal to x square q1x times q2x plus x times q1x plus q2x plus 4k1 k2. And this is also obviously belongs to S, because constant term here obviously even. So polynomial with even constant term be a subring. To prove ideal test, let consider fx be arbitrary polynomial in zx, and we have to prove px times fx would be belongs to ideal. Here consider fx equal to xgx plus L, where L be any integer. Then px times fx is actually similar to x square px times gx plus 2kx gx plus lx qx plus 2kl, which we can write easily x times x px gx plus 2k gx plus l qx plus 2kl, which also be an constant term even polynomial. So px times fx belongs to ideal. That means our proof has done polynomial with even constant term be an ideal in zx. Okay? Consider other example. Consider such px in zx such that p prime 0 equal to 0. We have to check, is this ideal? To prove ideal, at first we have to prove, is it subring? Consider this set as capital I, and consider two polynomial means px and qx belongs to I such that p prime 0 equal to q prime 0 equal to 0. Then px minus qx prime at the point x equal to 0 equal to, by rules of derivative, it would be p prime 0 minus q prime 0, and p prime 0 equal to 0 and q prime 0 equal to 0. That means 0 minus 0 equal to 0. Therefore, px minus qx belongs to I. Okay. Now for suffering test, we have to check their product be member of capital I. So Px times Qx prime at the point x equal to 0 equal to, by the rules of derivative, this is equal to P prime 0 times Q0 plus P0 times Q prime 0, and put the value, this value equal to 0 and this value equal to 0. That means this product is equal to 0, and that implies obviously Px times Qx belongs to the set I. That means I is a suffering. Now we have to check ideal. I is a suffering. Now we have to check our final category of ideal test. Consider Px be any polynomial from the set capital I, and consider a arbitrary polynomial fx from in Zx. Then we have to check Px times fx belongs to I. That means Px times fx prime belongs to I. We have to check it. And by the property of derivative, Px times fx prime at the point x equal to 0 is similar to P0 times f prime 0 plus P prime 0 times f0. But this part is obviously 0, but it is some polynomial which is at the point x equal to 0 is 0, but this does not necessarily their derivative equal to 0. If we consider Px equal to 7 and fx equal to x, then notice f0 equal to 0 obviously, but P0 times f prime 0 is equal to 7. Are you getting the condition? That means this is always not equal to 0. For such polynomial, Px times fx does not belongs to this I. Therefore, we have got an contradiction. I is not always be ideal. Are you getting? This is very important for any competitive exam. Now I will look one quotient ring Zi modulo ideal generated by 2 minus I. This is very interesting quotient ring. Here the elements are look like a plus ib plus 2 minus I, where ab belongs to integer. We all of us know this quotient ring is such type. Now here I will say distinct quotient of this ring, and in this quotient ring these two quotients are always equal, because here 2 minus I will observe by this ideal. So this is equal. We all of us know it. And here actually 2 equal to I, because if we add both sides I plus ideal generated by 2 minus I plus 2 minus I plus ideal generated by 2 minus I, which is equal to I plus ideal generated by 2 minus I plus 0 plus ideal generated by 2 minus I. If we apply addition of two quotient ring, then this would be I plus 2 minus I plus ideal generated by 2 minus I, which will be equal to similarly I plus 0 plus ideal generated by 2 minus I. And after cancelling I, this value equal to 2 plus ideal generated by 2 minus I, which is equal to I plus ideal generated by 2 minus I. Since these two left quotients are equal, so we can tell in this quotient ring 2 equal to I. Are you getting why 2 equal to I? Okay. For example, if we consider the element 3 plus 4i plus ideal generated by 2 minus I, then this value would be in this quotient ring 3 plus 8 plus ideal generated by 2 minus I, which is actually same as 11 plus ideal generated by 2 minus I. Means in this quotient ring, these two quotients are be similar. Are you getting the structure of this quotient ring? Well, now for this quotient, if we square both sides, that means if we square 2 plus ideal generated by 2 minus I whole square equal to I plus ideal generated by 2 minus I whole square, then this value will be 4 plus ideal generated by 2 minus I, which is equal to minus I plus ideal generated by 2 minus I. By the property of multiplication of two quotient, because this is, we can write this left quotient as 2 plus ideal generated by 2 minus I times 2 plus ideal generated by 2 minus I. Then use the multiplication of two quotient. Since two left quotient are same here, so we can write 4 equal to minus 1. That means in this quotient ring 5 equal to 0. Getting the structure of the element in this quotient ring. So I have got these two quotient are here equal. So also we can write 11 plus ideal generated by 2 minus I equal to 1 plus 5 plus 5 plus ideal generated by 2 minus I, which is actually same as, since in this quotient ring 5 is equal to 0, that means this is equal to 1 plus ideal generated by 2 minus I. Therefore, in this quotient ring, actually the distinct element are 0 plus 2 ideal generated by 2 minus I, 1 plus ideal generated by 2 minus I, 2 plus ideal generated by 2 minus I, 3 plus ideal generated by 2 minus I, and 4 plus ideal generated by 2 minus I. Other element of this quotient ring we can write in this way. So only these are different element. So actually this quotient ring is actually isomorphic to the subgroup Z5, because here this quotient ring only contain 5 distinct elements. So one interesting fact of this quotient ring, if A plus IB plus ideal generated by 2 minus I equal to 0 plus ideal generated by 2 minus I, then that imply obviously A plus IB belongs to this ideal 2 minus I, and here this is, since this is the principal ideal, so we can write it as A plus IB equal to all multiple of 2 minus I, that means C plus ID times 2 minus I, where C and D belongs to integer. If we multiply this part, then this would be 2C plus D plus I times minus C plus 2D. Okay? And by equating, this is equal to A equal to 2C plus D and B equal to 2D minus C. If we think this part as a vector, then obviously the vector AB equal to C plus minus 2 plus 1 plus D times 1 2. That means this vector AB be combination of these two vector. Vector actually look like this is the -2 1 vector and this is the 1 2 vector, and AB vector actually the linear combination of these two vector. And when I will see in my vector algebra class, then I will say this combination actually the orthogonal basis on the plane. Since the vector AB is combination of these two vector, this is actually look like this type. This will be extend. So this is the clear idea about the quotient ring Zi modulo ideal generated by 2 minus I, which is actually isomorphic to the group Z5. Now consider a mapping phi from Zi to Z5, where Zi means just Gaussian integer, and the mapping is look like phi from Zi to Z5 such that phi of A plus IB equal to, since in this quotient ring I equal to 2, that means this mapping is look like A plus 2B. And here obviously this mapping be ring homomorphism, just check it on self, this is very easy method. And the kernel phi equal to set of those Gaussian integer such that A plus 2B equal to 5k. And this is actually set of all Gaussian integer which is multiple of 1 plus 2i. And obviously we all of us know kernel be ideal. That means here the ideal would be the cyclic subgroup generated by 1 plus 2i. Ideal obviously principal ideal because it is generated by only single element. And in my above question was ideal generated by 2 minus I. This is, if you multiply this by minus I, then this would be 2 minus I. And since this is the principal ideal, so if A plus IB belongs to ideal generated by 1 plus 2i, then obviously all multiple of 1 plus 2i be the member of this ideal. That means this is actually look like C plus ID times 1 plus 2i. After multiplying, this would be C plus 2CI plus ID minus 2D. Then this would be C minus 2D plus I times 2C plus D. That means A plus 2B equal to C minus 2D plus 2 times 2C plus D. And this part would be multiple of all 5. So this is equal to 5x. Ring isomorphism theorem, we can tell Zi modulo ideal generated by 1 plus 2i is isomorphic to this set Z5. And this is because here the image is all multiple of 5. Here 0 is equal to 0, 1 is equal to 1, 1 plus I is equal to 3 and 2 plus I equal to 4. These are distinct element of this quotient ring which is isomorphic to the group Z5. Okay? OL.